And as you guys are aware that connections usually, we have two types of connections. We have bolted connections and we have welded connections when it comes to structure steel. Elizabeth, you just joined. Elizabeth, you're here. All right. So in bolted connections, I'm going to start here with showing you a column and a small beam, and this column is spliced, which means the column here is extended, but because of size, it needs to start and stop. So here, this column stops, and then the other column is going to start. To provide continuity for the column, you have here the column flanges, so you have two flanges, and then you have a web in the middle. So to provide this continuity, you need to have a plate so that you ensure the continuity of the flange on both sides. And in this picture, as you see here, you have a face plate. It is attached to the flange of both columns, above and below. And also in the back of it, you see also another plate. So the plate here is continuous. And then you have plenty of bolts to connect between the flange of the column itself and between the splice plates. So what's going to happen, the force, whether it's going to be tension or compression, let's say it's going to be in the top flange, and then goes to the plates, and then comes back to the bottom flange. In order for this to do it, it needs to go through all of these bolts. Same thing for the web. If you look here at the web, you're going to see a plate, which is shown right here, and you have also some bolts here to connect between the web of the column and between the plate. Most likely, in this case, I see here that you're going to have here two plates, one plate on each side of this column web. You have another connection here for two braces, so this is like a brace frame. And one of these braces is going to be continuous. You don't really need to interrupt. The other one here, you need to interrupt it because the presence of this brace in the same plane. So what you need to do is to put a gusset plate. So this plate here is called a gusset plate, and this plate comes welded in this brace. So when it comes from the shop, it's going to be welded, and then in the field, you're going to be attaching this plate to the other brace. Another bolted connection here. Here's a beam, a column, and here's the beam. And then you have a face plate. This face plate is welded to the beam itself. So this beam is fully welded to this plate. And then they bring the assembly, which means this plate with the beam, and then attach to this column with this 4 lines of bolts. This beam here is going to see some moment. Meaning, let's say at one point you're going to have tension on this side, and then you're going to have compression on the other side. Tension meaning you're going to have a force coming this way, and compression is going to be coming that way, if you have a moment. So what's going to happen, all of these bolts, they're going to see tension, because now you apply tension here, you pull this out. At the same time, this side is going to be seeing compression. In the same time, also, you may have shear on this beam. So the shear direction, let's say, is going to be coming this way. So in this case, this bolt here is exposed to combine tension and shear. While on the other side, all bolts is going to be exposed to shear. But when it comes to compression, compression is going to happen by bearing of this plate to the column. So actually, bolts in this case is not going to see any compression. Bolts in this case would see some tension and shear. The top bolts here, they're going to be seeing only shear forces. This here for eccentric brace frame. So this also a brace and this another brace. But the brace itself is composed of 4 angles. If you look here closer, you're going to see here 1, 2, and then 3, and on the other side you have 4th angle. And all of these angles, they are attached to this gusset plate. and the gusset plate is welded to the beam. So first we have this beam, and then we have two gusset plates, and then we have two braces, one on each side. Again, the brace itself is composed of 4 angles. So when they ship this from the shop, from the fabrication facility, and before they ship it, they weld all of these plates to the beam. So this here, this is what we call a stiffener plate. Look here, this is what we call here a stiffener plate. So a stiffener plate is going to be a plate that's going to be within the beam itself. And the reason that we have this stiffener plate is to stiffen the web of this beam. And this stiffener plate is going to be welded to the beam itself. Also, this gusset plate is going to be welded to the beam. All of that is done in the shop. They ship this beam separate from this braces, and once you receive it on the site, you're going to start here to attach these braces to the gusset plate with all of these bolts. Usually braces are exposed to axial load. They don't see moment. We don't design them for any moment. Meaning that you are going to have here either tension or compression. So I'm going to say here, let's say that this is going to be exposed to compression like this. And then this side, let's say it's going to be exposed to tension. So the member itself as a brace is going to be seeing compression, and this member itself is going to be seeing tension. Now the question is, how would you transfer the force, whether it's going to be compression or tension, to this beam? So I'm going to say load path. First, this compression is going to be in the 4 angles, on all of these 4 angles. Now we need to transfer them to these bolts, these 2 lines of bolts or 2 rows of bolts through shear. So the bolt itself here is going to be seeing some shear force only. And then after that, the force is going to get moved to the gusset plate, and from the gusset plate through the weld to the beam itself. Same thing applied to this side. The force here is going to be tension. It's going to get transferred to all of these bolts as in shear, and then from these bolts as in shear to the gusset plate, and then after that to the beam itself. This here, it shows the bottom of this brace. So at the bottom of this brace, you're going to see a gusset plate welded to the beam and welded to the column. And you're going to see this is going to be the brace as in 4 angles. So again, if I have here some tension force, like in this direction, what's going to happen? This tension force is going to get transferred to all of these bolts through shear. And from the bolt to the gusset plate, also in shear. So it is true that the member itself is exposed to different force like tension or compression, but the bolts here is going to be exposed to and experience shear force only. Let's go back here to the first sample that we looked at, the first picture. If this column here is going to be exposed to tension, so I'm going to say here, here's the first force, here's the second force. Now this tension force is going to be transferred through this plate, through all of these bolts, and this is going to happen through shear. So the member itself is going to be seeing here tension, bolts is going to be seeing shear, and then the plate also is going to be seeing some tension. On the other side of the column, this here exposed to compression. So what I'm saying is, this column here is going to be exposed to moment. So the moment is going to be causing tension this side, compression this side. What I'm trying to get to, some members, they see pure potential compression. Some members, they see moment. At the end, usually all of these bolts is going to be exposed mainly to shear plus some tension. So the type of forces that our bolts is going to be exposed to is going to be mainly shear. It's going to be number 1, this is going to be the major item, plus some tension. But if you have any compression, like in this case here, bolts not going to be seeing any compression because compression is going to happen by bearing of the steel plate to the column. So bolts here will not see any compression. Same thing that we're discussing. Here's a brace connected to the column. Tension force is going to be coming this way, let's say. To transfer the force from the brace to this plate is going to be going through this bolts as in shear. So since you have here one angle, you're going to have the force coming, and let's say this force is equal to 100 kips. It means that each one of these bolts is going to be seeing 50 kips. So you're going to be seeing here the same force equally. After that, you're going to have here this is like a T shape, if you like, or maybe this like couple of plates. Couple of plates means you have here this plate, and then here's the other plate. So in plan view, if you like to cut a section through it, let's say I cut here a section like this, right? You're gonna see here one plate is gonna be coming like this, and here's the other plate. This is gonna be in plan. Now we're gonna have here a few bolts to connect between this plate and between the column. So my bolts is gonna be running in this direction. I'm just showing here a line. Length of the bolt here is not an issue. So if the tension is coming this way, I'm gonna say when it comes here to transfer the force between this plate, the face plate, and between the column, you're gonna have two components of this force. One component is gonna be coming like horizontal component, and the other component is gonna be like this vertical component. So what's gonna happen? I should be able to resolve this brace force into two forces. One of them is gonna be horizontal force, other one is gonna be vertical force. And both of these two forces, they need to be transferred to this column. So what's gonna happen? This force is gonna be causing shear on all of these bolts. So these 4 bolts, maybe I have another line of bolts, so I'm gonna have here a total of 8 bolts. They're gonna be exposed to shear from this vertical component of the force. While this force here, this horizontal force, is gonna be causing tension in all of these bolts. Because in plan view, this force is gonna be like this. They're just pulling all of these bolts out. While this vertical force, which in this case is going to be shown as point, is going to be causing shear on all of these bolts. Okay, how about this connection? What's happening here? This is a hanger. You have a beam, and then you have a T shape. This T shape is going to be very similar to this. And as you see here, the force is going to be coming in this hanger as in tension, very standard. It's going to be going through these 4 bolts. So all of these bolts is going to be exposed to shear coming from this tension force. And with that, the force is going to get transferred to the T. The T is going to be this section, which is this box. It's going to be very similar to this guy here. You have horizontal plate and a vertical plate. Now the force is going to get from the hanger to the bolts and shear. And then after that, from these bolts to the plate, the vertical plate. After it goes to the vertical plate, now it goes to the horizontal plate. And now after this, it goes through tension to this vertical bolts. As it says here, this bolts is getting shear, while this bolts, all they are going to be in tension. So it is true that the member itself, like the hanger, is exposed to tension force. Some of these bolts is going to be in shear, the other bolts is going to be in tension. How about this combined shape? You can see this shape is going to be very similar to this shape, this picture that you're looking at. It's going to be very similar to it. You have a shear and also you have a moment. So this shear is going to be going through all of these bolts, the 3 bolts. Now the force is going to get transferred to this angle or this T shape. Now after it goes to the bolt, it's going to be going to the T, and this T looks like it's welded to the column. So now this vertical force is going to get transferred to the column. How about this moment? What's going to happen for the moment? This moment is going to be resolved into a tension and a compression force. So this is going to be your tension force, and this here is going to be compression force. This tension force is going to be going through the top T as in shear. And then after that, it goes to the T. And from the T is going to be going to the column flange through tension. So first is going to be coming from the beam itself as in tension through shear to the L shape or to the T shape, and then from the T shape is going to be going in tension to the column through these bolts. While at the bottom, look here at the bottom, here's the T shape. This compression force is going to get transferred as in shear to the bottom T. After that, these bolts, they're not going to be able to see any compression because compression here is going to happen by bearing of this T to the column directly. So the bolt's not going to be able to see it. So as you see here, I didn't try to take this vertical force and transfer it through both of these two bolts or through these two bolts and these two bolts top and bottom. So usually the force as in shear, when it is in the web, you try to connect it directly to the column so that the shear force itself is going to get transferred to the column directly. It's not going to be going to the flange. And usually the flange is getting exposed to tension compression because this is what's taking the moment. So in this case, you need to have separate connection for the top and bottom flange to the column. All right, so what happened when you have bolt and shear? As you see here, we have two plates. Here's one plate, and here's the second plate. This plate here exposed to tension. This plate here also exposed to tension, but this is going here upward, the other one is going downwards. At the beginning, before you start to apply the load, you don't have here any gap. So the bolt is going to be like this, and the plate through the hole is going to be right above it and below it. So in this case, you should have an equal gap top and bottom. And also here, you're going to have an equal gap top and bottom. Once you start to apply the load, some slippage is going to happen. So the two sides or the two surfaces are going to be sliding top of each other. Now, all of a sudden, you're going to have a full contact between this plate and between the bottom of the bolt because you start to pull this plate up. Same time, you're pulling this down. So this gap here is going to close. And bearing and contact is going to happen here in the top. And the gap is going to be at the bottom. So in this case, we call it that the force here is transferred through the bolt by shear. But when the bolt touches the plate, it's going to be by bearing. Someone's going to say, what does it mean by that? I'm going to say it means that right here along this section of the bolt is going to be exposed to shear force and shear stress. But on the bolt itself, you're going to have some bearing. If you want to think about it, you're going to have here bearing forces and bearing stresses. Same thing from the other side. If you like, you can come here and say, this is going to be bearing here. This is going to be bearing forces and bearing stresses. So if you want to understand it more, you say, forces come from here. It's going to be pulling the entire plate down. Once the plate here is going to be closing the gap, it's going to be bearing on the bolt. Now the force is going to get transferred to the bolt. Now it's going to be transferred through the bolt in this section through bearing, and then all of a sudden now it needs to go to the other side of the bolt. And this has to be in shear. Now you are shearing off, you're trying to shear off the bolt itself. Now the force is giving the bolt as in shear. Now once no gap is going to happen and bearing is going to happen between this bolt and between the bottom plate, bearing is going to start to happen and the force is going to get transferred to the other side. In a case like this, we call this single shear. Why a single shear? Because you have a single section of the bolt that's exposed to shear. So through the bolt itself, it's going to be only one single section of the bolt exposed to this shear force. Let's look here at double shear. What does it mean by double shear? Double shear is going to happen when this big force, and we used here the term P, or this symbol P, for this big force, it's going to get transferred into two forces. So in here on the top, you have one plate. So this here is going to be one plate. And on the bottom, I have here two plates. This happens a lot. When you have a gusset plate, then maybe you have a T. It also happened like through this. If you look here at this bolt is going to be the same idea. Because here you have the flange, which is like one plate, and here you have two plates. One is going to be right, the other one is going to be left. Also in this case, when you have four angles this bolt here is going to be going through one angle leg, from the other side one angle leg, from the middle you have this gusset plate. So I'm going to say in this case, here's the force, one half of the force is going to be in this side, other half of the force is going to be in this side. So you have one force coming this way, the other force is going to be coming this way. So this force is going to get transferred to this bolt by bearing. Now which side is the bearing? It's going to be in this side. You have here some bearing. Now the force now is going to be through the bolt itself. It's going to come to one section. It's going to be exposed to shear, which is this section here. So this section here is going to be through shear. On the other side, at the same time, you have one half of the force also is going to be coming in this side. It's going to be also transferred by bearing on this side of the bolt. What's going to happen after this? After this is going to get transferred here through this section of the bolt through shear. So now you have two like double shear action. Why double shear action? Because for the same bolt here exposed to double shear. And then after this, the entire force here is going to get transferred to this top plate through bearing, and the bearing is going to happen here. So now you're going to have bearing, and look at the gap. The gap also is closed. Now from here you have one half of the force, one half of the force. On the top you're going to have the total force. Okay, now I guess this is like you're utilizing and you're using the bolt in a more efficient way than the single shear. Because now you have the same plate, you have one bolt, so it's going to be the same bolt, but in this case, you have two surfaces to cut through if you like to shear up this bolt, while in this case, you have only one single surface. But here you have just one plate, you have another plate, here you have two plates versus one plate. So now we need to understand which situation we're going to be using single shear, which situations we're going to be using double shear. I'm going to take you back to the pictures. If this is only one angle, and this is going to be only one plate, I don't have a chance here to do double shear. It has to be single shear. My only chance to have here double shear, if I have one angle in this side and the other angle from the other side of this gusset plate. This is what we call here gusset plate. Okay, how about here? Here I'm going to say if I have just one angle, just this is like an angle here. If it's going to be only one angle and one web, this bolt is going to be exposed to single shear. But if you put a similar angle to this from the other side, means we're going to have two angle legs and two web, so it's going to be double shear. How about here? This looks like a channel. If you look at this section, like a channel. So how the channel looks like, it's going to look like this. In section, if I cut the section through it, it's going to be something like this. Of course, it's going to be closed. So if you have a channel this way, you can also attach plate to the back of it. This is exactly what we're doing. I'm cutting the section through it. So I'm going to say, in this case, I'm going to have single shear because any bolt is going to be just connecting the plate to the web of the channel through one surface for the shear. But if you give me two channels, if I'm going to have here one channel in this side, another channel on the other side, and then you have one single gusset plate, in this case, I'm going to have here double shear case. How's that? You're going to say, here's one channel. You draw here one quick channel. So here's going to be one channel. Here's the other channel. And let's say that I have a plate in the middle. Now start to put some bolts. Now, if this channel is going to be seeing tension, and this tension force needs to be transferred to this bolt. It's going to be going through two shear sections. So in this case, I'm going to be calling it here double shear bolt. Okay, now I guess we understand the single shear versus double shear. Now the other thing also that you need to know about installation bolts. Once you put the bolt, you need to tighten this bolt. You cannot just leave it loose. Otherwise, with any vibrations, going to get really loose, and you cannot really use it. So we have two types. We have this snug type. So we call it here snug type bolts, if you like. So this is going to be here snug tight bolt. Or we have it slip critical. That's what we call here slip critical. Sometimes they also call it pre-tension. We need to understand the difference between the two and how they affect the strength of the bolt. You can say, let me go back here to this connection. You can say, let's look here at this connection. If I just do snug tight means that you're going to be applying here some little bit of a torque. So you are causing here some tensioning to the bolt. You're just making it tight. This is going to be the first one. And in this case, transfer of the force is going to be happening through this bearing process that I was just talking about. The other method of doing it is when you have slip critical, which means that you apply pre-tensioning. Pre-tensioning means that you apply lots of tension force on the bolt. How do you apply the tension force? By tightening this nut a lot. You don't just tighten it like snug tight, but you're going to apply lots of torque. When you apply lots of torque on it, you're going to be putting lots of tension on the bolt. You're going to have high friction between the head of the bolt, between the nut, and between the two plates. And in this case, transfer of the stress or the force from the plate to the bolt is going to be happening through friction. And also transfer of the force from a plate to a plate is going to be happening through friction. And the friction is going to happen here on both sides of the plates. And in that case, I don't really put my force values, but I don't use my force values based on the bearing. Bearing is not going to be an issue. Why? Because I applied lots of force on this nut by torquing it and apply here lots of friction between the two plates. And the force transfer is going to be happening by friction. This is going to be a complete different type of performance of the bolt. And it's going to be up to you. If you're doing here gravity member design, it's going to be all by bearing, which means that you're going to be going here with this nut tightening. So if you do gravity loading members, like for example, beams connected to some other columns or some other beams, or a beam connected to a girder, it's going to be like snug tight. If you're doing seismic design and seismic analysis, let's say for some connections, it needs to be strip critical, which means that you really need to apply some pre-tensioning to it. So in our business here, in the calculations and the examples, we're going to be doing this snug tightening. We don't really need to use the strip critical. And you need to understand that this bearing of bolts, the bearing of bolts against the plates, is going to give you higher strength value than the slip critical. Let's say the snug tight for some given bolt, let's say it's going to be maybe 30 kips. For the slip critical, it can be maybe 25 kips. This number, just for sake of discussion, doesn't mean anything. It's not accurate numbers. I'm not talking here about the accurate number. And just, this is going to be also based on the size of the bolt and the grade of the bolt, the material of the bolt. As it says here, pre-tensioning will not prevent bolt slip at higher seismic loads. It will not stop it totally. But when you design, the strength of the bolt is going to be based on slip critical in seismic connections. Now, this is going to be the bearing mechanism that I was just talking about, which means a snug tightening. And if you look here in this case, here's the force in one plate, the force on the other plate. So this plate here is going to see tension, and this plate also is going to be seeing tension. But at the end, the force is going to get transferred through shear right here at the interface between the two plates through the bolt itself. Now, if you cut a section through here, if you just imagine that I'm going to be cutting a section through here, and looking right or left. This is exactly what you see. Here's a plate, and here's half of the hole, and the bolt is going to be running vertically through here. Total force is going to be equal to P. So here's the total force from one side is going to be equal to P. You can call it here this P is going to be the same force. When you cut through the hole here, it means that you're going to have 1/2 of the force in both sides. This is going to be here P over 2 and P over 2. And these two forces is going to get transferred by bearing to the bolt. So 1/2 of this bolt, which means one side of the bolt, is going to be exposed to the full force P. And you want to be sure that this bolt is strong enough in bearing. Otherwise, this bolt is going to get damaged. So the stress that you're talking about here, which is a bearing stress, is going to be equal to the total force P divided by this contact area. This contact area is going to be equal to this length of this arc, which means pi times d divided by 2, 1/2 of the circle perimeter, divided by the plate thickness. Okay. How about in pre-tensioning? What happens in the pre-tensioning? Now you start to apply some force on the bolt itself, but you don't want it to get to the yield point. So let's say that you have two types of bolts. You start here to apply some tensioning at the beginning. So what does it mean by that? If you apply any extension to the bolt, and let's say for some given extension, let's say this extension here is equal to 1/32 of an inch. You can say, okay, 1/32, this distance here is going to be equal to 1/32. And you have this force in the bolt versus extension of the bolt. So here, this is going to be extension, elongation, and this is going to be here the amount of force that you put to it. If you know the modulus of elasticity, which means the slope of this line, you can see here, if you have E value for the bolt material itself, so you can say, I applied this much tension or extension to the bolt, and with that, I was able to get this much force on it. We said, okay, I understand. And use the E for the steel, roughly, we say maybe 29,000, maybe 30,000, maybe 28,000. So some given value that we are going to be working with. So, okay, good. Now, if I have two different type of bolts, and I start here to apply lots of elongation, look what happened, like in this case. Each bolt is going to develop different force from the other, just because each one of them is going to be yielding at different point. So if you have two different materials, and you have the same bolt diameter, you start here to apply a tension to it, which means some elongation. You're going to be extending the bolt by torquing or twisting the nut. Now, once you start here to torque the nut, it's going to apply here elongation to the bolt, and you're going to be developing some force in there. Now, take the force that you applied there and divide by the contact area between the nut and between the plate, or between the head of the bolt and the plate. Which one? I'm talking about this contact area, not this contact area. I'm talking about the process of applying the pre-tension. Now you have some contact area between this bolt head and between the plate. Now take this pre-tension force divided by this area. It's going to give you some stress. This stress is going to be as in compression in both sides. You're going to have some compression stresses here, compression stresses there. Now you ask yourself, how about the friction resistance of this connection? I'm going to say friction resistance, if you like to call it R, is going to be equal to mu, which means coefficient of friction, multiplied by what? By the amount of pre-tension force that you apply to it. And this pre-tension force, I'm going to call it here pre-tension force, PL, for now. So here this R is going to be like a resistance. So let's say for sake of discussion, I put a force here, like pre-tension force, and pre-tension force in this case is going to be compression. So I'm going to say this force, which is going to be throw a number there, you can say this force equals, let's say 20 kips. So this 20 kips is going to be coming as a compression. Now coefficient of friction between the steel and the steel, I'm going to assume is going to be equal to 0.3 mu, which is coefficient of friction, or let me just call it here coefficient of friction. Let's say it's going to be equal to 0.3. It means that when you apply this force of P, you're going to have a coefficient of friction multiplied by the friction force, the applied friction force. It's going to get here frictional resistance. So I'm going to say R here is going to be equal to 20 times 0.3. It's going to be equal to 6 kips. As long as this force P is going to be lower than 6 kips, the connection is working fine. Nothing is wrong with it. When the force here is going to be approaching 6 kips and a little bit higher, some slippage is going to happen. Now it's going to start to slide. And with that, we're going to say the slip critical connection strength is going to be equal to 6 kips. When you do your design, you be sure that you keep the force within each bolt to be, let's say, within 6 kips. This is going to be for the slip critical. So the slip critical is going to be based on shear resistance and frictional resistance between the bolt and between the plate itself. Does this make sense? Any questions? All right. Now, how do you control the amount of pretension that you put in there? You're going to say, well, it is here that you're going to have a torque wrench, and a torque wrench is the wrench. It has a socket, and you start to apply to rotate it. It's going to get exactly how much torque you put in there from the resistance. Or you can do it by number of turns. When you take the nut, you start to turn it. So here, for example, it says, here's the nut rotation in terms of turns. It's going to be quarter of a turn, half of a turn, 3/4. Now it's going to be 1 turn. Now you start to do it by turn, which means that you start at the bolt in one location. Now you start to rotate it after you do the snug tight. So all of this is going to be after you do the snug tight. After the snug tight, you're going to be taking it, and let's say you start by drawing a line, like a vertical line on the nut. Now you start to make it horizontal line. Now the amount of rotation in this case is going to be 9 degrees. 9 degrees means what? It's going to be quarter of nut rotation, or quarter of a turn. Now in this case, now you look here at the amount of force that you are able to develop in the bolt. Look at this amount of force. You're talking about maybe 34 kips, or maybe 33 kips. Now once you take it here to have a turn, the type of bolt is going to be a big issue, a big deal, because you're going to be reaching the yield point for it. But if you keep it like a quarter, you're still in the elastic range. After this, you're going to be going in the elastic range. And this is the reason that you see here 2 types of bolts. Like, for example, this type of bolt, we call it ASTM A490. And this here, ASTM A325 bolts. And look at the difference in the amount of force that you've developed in there. So I'm expecting here, if I'm going to have a higher grade bolt, expose it to the same amount of rotation or turns, I may be able here to get higher force. And this bolt extension or the bolt pretension force is going to be higher than that for the low grade. And when you have here higher pretension force, this is going to help you out in the slip critical. Why? Because the slip critical is going to be equal to the amount of pretension force times the coefficient of friction. So when you have here higher grade bolts, right, with higher, I'm going to say, model of elasticity. So for the same amount of rotation or turns that you apply to the nut, you're going to have here higher pretension force. And once you have a higher pretension force, it means the slip critical force or strength is going to be higher than that for the low strength bolt. Okay. We have this type of bolts that they call tension control. And this usually happen in these 2 types of bolts, the 325 and the 490. We call this high strength bolts. So we have conventional strength or regular strength, which is called machine bolt. So when you hear here the term machine bolt, you know this like the standard bolt that you see if you like to buy any bolts from any place. It's gonna be the cheap bolts. As long as it's gonna be steel, it's not aluminum, it's not plastic bolts. If it's a steel bolt, it's gonna be A307. So let me type it here. This is gonna be like the A307 bolts. It's gonna be like the machine bolts. Call this machine bolts. It's gonna be like the cheap bolts. If you are doing any connection that involves maybe some wood with it, you're gonna be doing A307. The reason is because the steel in this case, you don't really need to have high strength steel or high grade bolts because you have wood connecting to it. So the wood is gonna be much softer than the steel. So you don't really need to go to any high strength bolts. Once you go here to 325 and A40, we're gonna call this high strength bolt. And from time to time, you're gonna see this high strength bolts. HS, high strength bolts. High strength bolts include 325 and 490. Conventional bolts or machine bolts is gonna be the A307 bolts. Is it okay? When do you think this is gonna be used? What is this? What's going on? I'm gonna say this happens usually in high strength bolts. So I'm gonna put it here. Standard for high strength bolts. And the reason is because now you'd like to apply the torque, but you're not going to be using a regular wrench. You're not going to be doing this by hand. And also, if you like to do here snug tight, you're not going to be doing it by hand. You need to have pneumatic wrench. Something is going to be like power wrench. You just apply to it. It's going to be most likely by air. It is non-electric. And in a few seconds, you should be able to tighten the bolt. Now, even for the snug tight, you need to have certain torque that you apply to it. So what's going to happen? Here's the two plates. Here's the bolt, the washer, and the nut, and this is going to be part of the bolt. If you look closely here at the bolt, you see the bolt. This is going to be the thread of the bolt, and here's the nut. And then after that, you see the shape of the bolt itself. It has like a weak section. It's gonna be right here, and then you're gonna have some like notches here through the rest of the bolt. Now, when you bring the wrench itself, it comes with two sockets. You have one big socket from outside that the nut is gonna be fitting in, and then you have a smaller socket that this shank is gonna be fitting in. Once you apply the wrench, the outer socket is gonna be going clockwise, and the inner socket is going to be going counterclockwise. It's going to be opposite to it. So when this is tightening, this is going to be kind of twisting the other direction. So this is going to make here tightening, this nut is going to move fast. This is going to be number one. And once you reach certain torque, this piece here is going to snap off. This is going to be sheared. Why? Because you apply twist in one direction, you apply here twist in the other direction. And this section is made so that it's going to snap right at this location. And once it snaps, this piece is going to come out at certain torque strength. And this is what we call here snug tight. So you can control this. So if you like to go here with some snug tight or pre-tension, you can design it according to this strength. Let me run this here for you.
Professor, we can't see.
Yeah, I know. Working on it. But do you hear anything?
Yes,
Yeah.
we do.
There it is.
So you have here few plates. You have top plate and bottom plate. You're gonna put here the bolt. Then you have the shank. This is the piece that I'm talking about. You're gonna put the washer plate, the nut, tighten by hand. This is gonna be the critical section. You bring the wrench, You hear the video?
Yes, we do.
Maybe all just hand tighten. You can bring now, this is going to be regular wrench. Still called hand tightening. Also a torque wrench. You see this? Control to certain amount of torque if you want to. Here's the wrench. This is electric one just for the lab. For the lab work. One is going counterclockwise and the inner socket is going counterclockwise. Let me bring it here. Just want you guys to look at this. You see, you hear the sound of the motor, but nothing is, because only the inside socket was rotating. This is the motor. Maybe the outer socket. Right, any questions or comments?
The order that he did the last process, it's there's like a rule to that, isn't there, when you're turning
Installation
bolts?
method series.
What was that?
I'm sorry, that was not me. That was the other video. Yes.
Oh.
Go ahead.
So there's like a certain like process in tightening them, right? It's like diagonal. You go diagonal first.
Yeah, it is like, you know, when you have, I don't know if you have ever replaced or see someone replacing a spare tire in a car. You need to go in a certain order.
It's the same concept for the plates.
Yeah, very similar to it. Yes. Yes.
Okay, cool.
All right. Hold on.
Installation method.
Just want to show you this quick. See the two sockets? This give you the inner one, this give you the outer one. So this one rotates counterclockwise, other one is rotating clockwise. And then snaps off this piece. So first he's just tightening it. Now this snaps off. Okay? We're good?
Yes, doctor.
Yeah. All right. It's good enough here. This is what we were talking about here for the slip critical, the pre-tension. So here's what happened. You start here to apply The twist or the torque to the knot is going to apply by its turn like tension on the bolt, and this tension of the bolt means compression on the plate, and this compression on the plate, if you take it, multiply the coefficient of friction, you're going to have this resistance between the plates and between the bolt and the plate, and this is how you get the slip critical values. Now, when it comes to bolt by bearing, the strength of the bolt itself is given by this equation here. The equation is simple. It's going to be a very simple equation that you need to use. Equation says phi Rn, which means the resistance. Generally speaking, the resistance is going to be equal to a phi factor of 0.75 times some strength value times the cross-section area of the bolt. And this applies to any bolt of any material. Now we have two types of bolt, generally speaking. We have bolt which is normal strength, like the A307. I'm going to write it here, machine bolts. We call this one here machine bolts, ASTM A307. Or it's going to be high strength bolts. And we have more than one type of this high strength bolts. So this nominal strength, we're going to see the table J3.2. This is going to be a very interesting table from the code, from the EGCE 36016. And this AB is going to be the cross-section area of the bolt. Not just the cross-section area that you do based on handy calculation. You say pi d squared divided by 4. It is not like that. You know, for each bolt, you're going to have certain cross-section area according to the ASTM number. And the phi factor is going to be 0.75. So the normal strength bolts, as we were saying here, is going to be the A307. And most likely we're going to be using this grade A. We're going to see the strength of it and all the properties. The high strength will include something like the A325, the F1854, 490, and then we have other also ASTM specifications for it. When you have the normal strengths or the conventional bolt, I'm going to call here conventional bolt, the A307, you don't really care where the thread is going to happen relative to the knot and relative to the plate, the connecting plates. But when you have high strength bolts, this is going to be an issue. We're going to have here in condition and X condition. I'm not going to be read it up here, but I'm going to show the pictures. It's going to be much clearer to us. Let's say the bolt here, there's two cases. Here's the in condition and here's going to be the X condition. So you have two plates, and this is going to be here seeing a force going upwards. This is going to be seeing force coming downwards. And same thing for these two plates. Now the shear is going to be going here by bearing, right? So each part of this is going to be exposed to some bearing. And then at a certain point, the force is going to get transferred through the bolt itself, as in shear. Same thing here. So the force is going to be going through this piece here. Now, if I have the same grade of bolt, so the bolt grade is the same. I'm talking here about, let's say, A325. What's A325? A bolt specification, certain type of bolts. Same bolt size. Which one do you think is going to be stronger in shear? Is it going to be N condition or X condition?
I think
X
X condition because it also goes.
Go ahead.
Because I think the X condition because the solid part goes into the other plate.
Okay. So what you're saying is because the shear section itself is happening through the shank, is not really happening through the thread. Am I correct?
Yes.
And most likely the thread is going to be weaker than the shank itself, the main bolt body.
I think so.
All right. Very good. So as we're saying here, if this is going to be happening in shear, this is going to be stronger than this. So let me ask you here, Teresa, how about if we have it as in tension? I have a tension force here on the bolt, right? Which one do you think is going to be stronger? The X condition, the X, or the N condition? What?
I think the N, because the ribs of the bolt will keep it from tensioning.
No, I'm going to be taking the shear force out. It's going to be only tension force here versus tension force here. Would that be any different?
Yes.
What's the difference between the two now?
I think the N condition will be better because something to do with the middle.
Well, the tension force here in the bolt itself, I'm talking about the bolt itself. The tension force in the bolt is going to be going through the threads, right? In the reduced section, right? And here also is going to be going through the reduced section. So what I'm trying to say here, there is no difference between the two cases, the N condition or the X condition when it comes to tension. Because the force is going to be going through the thread anyways. And the thread is going to be like reduced section. So let me assume here, this is going to be the big bolt diameter, right? The original bolt diameter. And the thread is going to be a little bit smaller. So I'm going to put it here smaller than this one. So let's say the bigger one is going to be the big bolt, right? And the inside diameter is going to be for the thread, because you're going to be cutting a little bit of it to build it this way. So when it comes to shear, and they have this X condition, now the shear section is going to be the big diameter. So I'm expecting that this X condition is going to be stronger than the N condition. And this makes sense. But when it comes to tension force is going to be going through the inner diameter anyways, whether you have it here or you have it here. Because now the connection between the bolt and the nut is going to be through the threaded section. So actually, there is no difference between N condition and X condition when you have tension. Difference is going to happen when you have shear. So the question
Okay, that makes sense.
What's that? Make sense?
Yes.
Okay, thank you, Teresa. Let me put here your name. Okay. So in the site, in the job site, because what's going to happen in analysis, I'm going to say, let me use here X condition. So I'm going to be using here high forces. So let's say for this bolt size, the strength is going to be 45 kips for some given size, for some given bolt grade. And in this case, it's going to be only 40 kips. You decided in your design that you're going to be doing the 45 kips, the X condition. How do you apply it on the site? How would you be sure that they install it this way and not that way? Because usually you're just going to have the bolt. When you buy the bolt, you just buy the bolt. The bolt is going to look like this. It doesn't say X bolt or N bolt. It's just a bolt. And the issue is when you install it, you want to be sure that this fang surface or this sheared section is going to be in the shank. It's not going to be in the threaded section. So what you need to do is to put the specification of the bolt on the plan, on your drawing, on the details. So for that, you're going to say, I'm specifying A325X. So the inspector is going to be going through each one of these bolts. It's going to be called X, and be sure that the sheared section is not going to be through the thread. It's going to be happening through the big shank or the big bolt body itself. This makes sense?
Yes.
And if you specify N condition, he doesn't need to do any inspection. Why? Because whether the thread is going to be happening here at the fang surface or is going to be happening through the big bolt itself, it doesn't matter, because now it's going to be N condition. Therefore, once you start here to specify X condition, you know there's going to be a little bit of additional cost to it. So if you have a chance to use N condition, go ahead and use it always. Unless you really have to use X condition, in this case, go ahead and use it. Okay. Here is a table taken from the EGCE 360-16, table J3.2. Nominal trends of fasteners and threaded parts. This here reminds me with the specifications when we were looking at different type of steels, and then we have F sub U and F sub Y. It's going to be very similar to it. And instead of that, I have here description of the fastener, what type of steel. Then I'm going to have here nominal tensile strength, F sub N, and what? In tension. This is going to be in tension. And this one here is going to be in shear. Okay. This is here for bearing type. I guess you guys know what's the bearing type, right? What's the opposite of bearing type? I have either bearing type or slip critical. I have either the pretension, which is a slip critical, or I have the bearing type. If you're doing gravity design, I'm going to be doing this bearing type, like beam connections and stuff like this. So in our course, we're going to be using this table. This is going to be bearing type. Fn, which means nominal trends in shear. It says here V. It's going to be nominal trends in tension. All right, now understand the difference between the two columns. So what do we have here for the description of fastener? Type of bolt. This is going to be here machine bolt, like the A307 bolt. And this is going to be F sub N T in tension in KSI. 45, here I have 27. So great, now I have the trends values. What do I use this Fn sub T and Fn sub V for? I'm going to be taking you here back to my equation. Here's the equation. This is going to be the Fn that you'd like to use. If you want to do the bolt in tension, use Fn in tension. If you want to find out the trends of the bolt in shear, you do this Fn in shear. And the phi factor is going to be the same, 0.75, times the cross-section area of the bolt. Now with that, I should be able to figure out the trends of any bolt size based on this equation. I see here for the A307, it just give me here two values. It doesn't say here N or X. But once you go down here to something called group A bolts, if you like to understand group A bolts, there is a certain section of the code to explain to you what does it mean by group A bolts. But as an example, it's going to be the A325. It's going to be the first group. It gives you here two different values. Look at this. 325, you have a case. In the code itself, when you open it, it doesn't say N or X, but it says when threaded are not excluded, which means N, case. And this is going to be the X case. Now look at the difference in the strength when it comes to the N and X case. If there's some difference in shear for the N and X case, you're going to say, yeah, here's the X case 68, and here says 54. Now, which one is stronger? You're going to say, of course, the X condition, which makes sense. X condition is going to be stronger. Why? Here's the X condition. When you're sure that the shear is not happening through the thread, so you're going to have your higher trends. Yes, 68 versus 54. But look in tension. Is there any difference in tension? No. Tension, when you have N or X case, you're going to have the same strength. Why? Because the force is going to be going through the thread anyways. So, okay, now that was group A. Let me go here to group B. What's group B? It says, like, for example, the bolt that's going to be called A490. Still going to be called here high trends bolts. Let me take you back just to refresh your memory here. It says high trends bolts is going to be like A325 and A490. What else? Let me take you back. Let me take you to this. Look at these two different bolts. I said that this is going to be here for high trends bolts. We have the A325 and the A490. Now I understand where these names, where did I hear them before? Now I remember. The A325 high trends bolts and also the A490 also high strength bolts, both of them. They're both high trends bolts, not just one of them. The A325, the A307 is a machine bolt, like the conventional or normal strength bolts. Okay, here's group B. We have also this group C. This is a new group, and this is going to be higher trends. Like, for example, it says F3043 bolts. So it's going to be again ASTM F, and then you have 3043. It's going to be ASTM A490. Look at the trends in tension. 113, same as 113. 68 versus 84. Look at this one. 90 versus 113. So look here. still high strength bolts, all of these, right? But you have grades. You have like the first level is going to be group A, little bit of a higher level, B, and then a higher level is going to be C. Look at the trends here in tension. It goes from 90 all the way to 150. So look at this, 45. The machine bolt that you buy from any store, the cheap one, is going to be 45 only KSI. When you look here at this high grade, it can go 3 times stronger. And look at this, 27 versus 113. Wow, this is a lot stronger. Now, there is some other bolts that's not covered under all of this. Like, for example, the F1554, there's something called here F1554. Let me add it. So I'm going to say here FASTM F1554, which is famous one. This is a famous one here that we use a lot for threaded rods. Now, you don't have the trends of it here. It is not an A307. It's not group A. It's not group B. It's not group C. But we still use it. So it is not one of these groups. And in this case, they say, well, let's look here for F sub U, ultimate strength of the bolt. And this applies here to lots of cases. It says take 75% of F sub U used in tension. For the N condition, use 0.45. The X condition, use 0.563. If you have an older copy of the steel manual, you're going to have completely different values. So these values, they changed, they increase it. It used to be lower than this. So this is something good. When you do a design for actual, I'm going to say people practicing, this means a lot because in many cases, you need to add little bit to the force, to the strength of the bolt. So you want to increase little bit the force or the strength. And this is going to be a very good chance here that we have higher trends in the tables. So I guess my equation is going to be simple here. You take 0.75 times the nominal strength times the cross-section area of the bolt. So good. Also in the steel book, now this is taken here from the code, from the 360 itself, right? The code, the AIC 360. But in the steel manual, you have this line table, table 7-1. It shows you here for single shear and double shear cases, right? And now this table is just one table, as if you take this piece and put it next to it. How is that? Here's the bolt diameter, 5/8, 3/4, 7/8, 1, and next to it is going to be 1 1/8, 1 1/4, 1 3/8, 1 1/2 inch. So you can extend the table this way if you want to. They divide this here for you. They say if you have group A bolts, I guess you know what's group A. If you're not clear, you need just to go back here and read it. They say, here's group A. My example is going to be 325, group B, group C. This is going to be A307, which means the normal trends, the machine bolts. And it says here not applicable. You don't have N and X condition. And then they split it here into N and X condition. And they give you the trends for each bolt for ASD and LRFD. And certainly you are going to be working only with LRFD. At this time in this course, we are going to be working on this. If you are looking for the nominal cross-section area for the bolt, you need to take it from this table. You cannot figure it out. You cannot say pi d squared divided by 4. You cannot do it. You just take it from here. Nominal strength or nominal cross-section area of the bolt, you take it from here. And same thing also from here. Look at this. Nominal cross-section area. This is what you need to use in the analysis. So now you have the nominal cross-section area. And instead of going back to your equation, you can just use it from here. So for example, I have 307, 1.5 inch bolt. How much is the strength for single shear? Yes, say 307, 1.5 inch bolt. Here's the strength. Which one do I do, LRFD or ASD? I'm going to do here LRFD. So let's give you this strength. Okay. Now this question to Teresa. Are you still there?
Yes, sir.
Okay. I'm going to say, I'm trying to find out the trends, which means phi RN. This is the way they call it. This is instead of phi, I just put here F. I'm going to say here, I'm looking for this phi RN for the following. I'm gonna have here 1/4 of an inch bolt, and the bolt would be A 325 N single shear. Can you get me PRN, please?